Hello, this is Dr. John, your physics and math professor, and today we're coming to you with another circular motion problem. Today we're going to talk about an amusement park ride, something at the country fair, which is called the Rotor, or the Gravitron, or the Starship 2000, or Mission to Mars, any of those things. And basically, here's roughly in perspective, it's a big round bin where people come. This would be the top view. Looking at the top from this view, people would come and they would stand up with their backs against the inside of this big round bin, this big round drum here, just like this. So here I've drawn the top of the people. This is the top of their heads and their hands where they're sort of leaning against the side like this. And then what will happen is this bin will start to spin around and the bottom, which is holding up their feet, will slowly drop out. And the pressure, the force that they feel to the outside, the centrifugal force that they feel to the outside, will pin them against the wall and they'll barely be able to move. Some of them will try turning around and maybe rotating, and then they'll have to come back into position when it slows down again. So I've given you some of the details here. This Gravitron has a radius of 5 meters, measured like this from the center out, and it makes 24 revolutions per minute. How many G-forces, how many times the force of gravity do the riders feel? We're ignoring the normal gravity we feel downward, just the gravity that we feel outward because of a rotation. Let me just review here really quickly what happens when you spin around like this. Say somebody's inside here. What will happen is, as you go around like this, you're going to experience an acceleration. Let's say you start off with a velocity in that direction at the top here. You're going to have to accelerate a little bit that way to get yourself moving like this. Accelerate a little bit more like this. So you're moving like this, and slowly your acceleration will take you all the way around the circle like this. Your acceleration always is toward the center. So I've drawn a radius like this. You're going to be accelerating like this toward the center all the time. This inward acceleration is called the centripetal or centripetal acceleration that must be carried on to keep this moving onward like this in a round direction. This is much like the acceleration in an elevator, where you're standing on an elevator and the elevator accelerates upwards. You feel like there's a force pushing you downwards. This is like gravity. Einstein said that the gravity created by acceleration is the same as the gravity experienced or created by a mass like the Earth. So this gravity, this outward force that you feel, which we call the centrifugal force, let me write those two down. So the centrifugal force, like a centrifuge, is the force you feel outward, and the centripetal acceleration is the force or the acceleration that you need to have inward to keep you turning like this. This centripetal acceleration or centripetal force is not a real thing. It needs to be created by something else. What is creating the inward acceleration? Well, obviously it's the structure of this thing, and the sides, the structure of the sides are keeping it together so that it's constantly, as it's spinning, it needs to hold together. It would tend to want to pull apart, but the structure of it and whatever metal it has holding it together is keeping it together. So that's what allows us to have an inward acceleration, which makes it feel like we have this centrifugal outward acceleration. That's what we want to measure. We want to measure how much their weight, their outward force, their outward acceleration, what they feel like that is. So I'm going to try to calculate this. How do we calculate this? Remember the old formula that we have? That is the acceleration centripetal is equal to v squared over r. This is the r measured from the center, and v is any speed. It's not the vector speed, it's just the absolute value of any speed measured at any point here along the circle. It's all going to be the same. The velocity, the magnitude of the velocity is not going to change. The vector direction of the velocity will, of course, change as you go around the circle. So to calculate this, we're going to need the velocity. How do we find the velocity? Well, velocity, very simply, is the distance something travels divided by the time. And the distance here is not given explicitly. You have the radius. So to find the distance, you'll just look at all the way around the circle, which would be the circumference. So the circumference around the circle is all the way around the circle from here to here is measured as 2 pi r. 2 pi times the radius. This is just simply all the way around the circle. So this would be the distance that you travel in the time that you travel it. Now, how long does it take to go all the way around the circle? What we're given here is 24 revolutions per minute. 24 revolutions per minute. If you recognize, this is like a frequency. This is like something per minute, because it's like hertz, sort of, except this is in minutes. We prefer not to have it in minutes, so let's put it in seconds. 24 revolutions per 60 seconds. So this would be revolutions per second now. This is the frequency. If you remember the period would be the number of seconds per revolution is the flip of this. So we would flip this the other way. Let's just do that. So it's 60 over 24. You can see pretty easily the 6 will go into the 24 like this, giving me 10 over 4. So that's going to be equal to 2.5. So the seconds, I'm going to write that somewhere over here. So that's how long it takes to go around once. That's the period, 2.5 seconds. And here is the distance it goes, 2 pi r. Let me write all these things in here so that we have them for us. So the distance it's going to go is 2 pi r, 2 pi, and r is 5. So that's 5 divided by 2.5. Notice this is 10 over 2.5, which is going to be 4. 4 times pi, 12.57 meters per second. That's very important. Too many significant figures, of course. We only have 2 here and 2 here, but always keep a couple more till right at the end. 12.5 seconds is the velocity, so we'll want the velocity squared over r. I'm going to erase a couple of things here and write this out, keeping this in mind. So here we have the centrifugal or centripetal acceleration. The acceleration toward the center you need to do to maintain this rotation is v squared, 12.57 squared over r. Quick calculation shows that that's 31.6 meters per second squared. This is what we wanted. Now, what is it that we were actually asked in the question? We were actually asked how many g-forces does the rider feel? Well, this is meters per second squared. Remember, the gravity of the Earth is around 9.8. So we'll take this divided by 9.8. So 31.6 divided by 9.8. Both of these are in meters per second, so we're just going to have a number at the end. It's going to be roughly 3. I'll just check my calculator and see what exactly it is. I'm getting 3.224 for that. We want this in 2 significant figures, so since this is smaller here than 5, we'll just go 3.2. So the number of g-forces that the rider feels is 3.2. Or if you're writing out the answer, you would say the riders in this amazingly fun ride will feel 3.2 times the acceleration of gravity against the wall. Of course, when the thing starts slowing down, they're going to start falling again in this direction, so the ground will come up before they start falling, and then they slow down and are able to walk out again. This is one of the most fun rides at the carnival. Really enjoy it. If you ever go to the carnival, you can actually probably do this calculation, roughly estimate the diameter or the circumference of your rotor or your mission to Mars, and then try to figure out how many g-forces you're experiencing. I hope that helped. If it did, like and subscribe, and I will see you in the next video. Bye-bye.